Okay, so hello everyone. I am Nandi from ISAR Kolkata, and for this course, study guides in organic retrosynthesis. I am the teaching assistant for that, and today is the first live session of this for this course. So I am starting now. So again, hello. I am Nandi from ISAR Kolkata, and for this course is study guide in organic retrosynthesis and problem solving approach. So I have planned to progress in this course like I am solving some previous year's questions for this course and some related questions for that, and which will be helpful for all of you if you want to solve the assignments of this course. So I am so let's start today's live session, and some of you have joined this in live, and some of you may have or will see in the offline mode later. So I want to emphasize that this is my email ID, and I am solving the question. And regarding the course, when the professor is giving the lectures, so if you have any doubt on that, you can directly mail me in this mail ID. So I will try to clarify the doubts in later classes. And in the live sessions who have joined, if you have any questions at any point, please stop me and ask, and in this way we will progress. So let's continue. So before starting the problem solving approach, so I want to emphasize one thing: this retrosynthesis, and we cannot begin this course without giving an homage to the pioneers of this field, who is none other than Izekuri. So you can see this book, The Logic in Chemical Synthesis. This is still the Bible for all of us, the organic chemists. So if you are really interested in retrosynthesis, total synthesis, I will encourage all of you to go through this book, and some of the problems may appear in are, are directly from this particular book. So this is Hijekore holding this book, which is written by him, and all of you may know that he won the Nobel Prize in 1990, and he is still a researcher doing his work, and so that's why I want to start this course uh, with an homage to him. So let's continue for our first problem. So for as this is the first live session, I would give you a quick recall of all the name reactions you have learned, or some of them probably are new for you, or you may already know some of that. So I will solve these questions to recall all these name reactions, and slowly we will proceed and cover the assignment part. So in this way we will progress. So this is the first question. You can see so this is our target molecule, right? So first question, they have want to know that this target molecule, how we can prepare from this starting material. So some of the notations you may already know, so if you have seen the uh, recorded classes. So this is the TGT, the target molecule, and this is starting material. So there are four options are given: Beckmann rearrangement, aldol reaction, Appel reaction, and Michael addition. So let's see what is Beckmann rearrangement. So for Beckmann rearrangement, the reagent is in H2OH. So here you can see uh, the lone pairs are like this. So due to alpha effect, this is more nucleophilic in nature, and it would attack the electrophilic center of the carbonyl group. So this is our keto compound, and NH2H would at first react with that and make this type of molecule. Sorry, here I have NH2H. So this lone pair is attacking like this. So in this way this is making, and after that nothing, just water elimination and making this type of C double bond N and OH. So this is how things work. So after that you may know in the Beckmann rearrangement we need to have heat. So with help of heat the rearrangement would occur. So this bond or this bond would keep, as both are symmetrical here. So there is no problem. Any of the bond you can rearrange and make this attack. So one thing also, in this heat we need to use some acidic source, or some we need to make this OH leaving group, so that this cleaving of this bond becomes feasible. So we need to make this OH as leaving group. For that H plus is generally used, any acidic source, and other things, other leaving group can be same in the same way, they can be also utilized. So after this rearrangement, what is the product is that here one positive charge is there, as this thing is rearranged, and this particular bond is formed. And here it is not like this. This lone pair can stabilize this positive charge and make this as C triple bond N moiety. Sorry, and rest of the things are like this. So now this is positively charged, and during workup or in reaction mixture water is there. So an easy nucleophilic attack can happen like this. So now what is happening? So nothing, just here double bond in OH, and it become one 7-member ring, and here after that nothing, ketoenol tautomerization would happen, and this particular CONH bond will be formed. So this you may already know that due to the stability of CO over that C double bond N, this form is preferred, and this is the product we have got. So as you can see, the answer is also A. So I want to also say a few things about the other things. So what is aldol reaction? You may already know, but still it is nothing but a CC bond formation reaction. So here what can be the things? So one like one acceptor is there, and another enolate we require, and in presence of base. Yeah, if you have any question you can ask, or please mute. Yeah, here in presence of base, enolate can be formed here, and this can attack here and make this CC bond aldol reaction. So this is not the right answer. What is Appel reaction? So Appel reaction, there are many variants of that. So I would I am writing one of the general forms. So Appel reactions are like the alcohols R1 and R2. Let's say, and you can see this is an chiral center. So let's say its configuration is R. So in Appel reaction, the uh, uh, general reagents are, sorry, CX4, and X are halogen molecules, Br, fluorine, and so on. And another thing is used is PPH3, and solvents varies. You can use different type of solvents and temperatures. So what happens here is uh, that one one CX and here X3, so PPH3. So this PPH3 can attack like this and form this PPH3 X complex, and you can see this is plus, and as it is attacking, so what it will be minus. So CX3 minus, and what is our substrate? I have written like an alcohol R2. R2. So this minus charge can abstract this proton and make it R1 O minus R2, and this is our another reagent. So this attack is also favorable. So like this, O PPH3 plus is there, R1 and R2, and X can leave as X minus. So X minus is there, and it is a leaving group. So you can see things are set for an SN2 reaction. So this can happen, and R1 X R2. So as it is an SN2 reaction, so inversion of configuration must happen. Inversion would happen. As I have said, I have assumed the configuration of this is R, so this should be S. So this is how the Appel reaction. And Michael reaction, all of you already know, but let me clean some of this. Yeah. So Michael reaction you may also know, but still as I am recalling everything, so I would do that also. So this is an Michael acceptor. So and any nucleophile which can attack this position, this particular position, and make this type of molecules. So this is an Michael reaction. So for that, some of the restrictions are there, that this nucleophile should be softer, not hard nucleophiles are used. If you use hard nucleophile like RMGX, so what it is, you may already know, this is Grignard reaction, Grignard or RLI. This type of hard nucleophile if you use, so this would do 1-2 addition, right? So this would if 1-2 addition is happened, so alcohol would be formed. So here R and OH like this. So these are not Michael reactions if the things are softer, like R2CuLi. So this is most commonly used. Copper 1, copper related organometallic compounds. For that, this nucleophile is much softer and would lead to this 1,4 attract. So if this 1,4 attract is formed, it is Michael reaction, and if 1,2 addition is happening, normal alcohol formation reaction. So this is the first problem, and the answer is A. So let's move forward for the next one. So this is the starting material, and this is TGT. So what is the transformation here? So there are four options. So aldol reaction, if I have discussed earlier, it is not an aldol reaction. In aldol reaction, we need to have one enolate. For that, one alpha hydrogen is required. But here, no alpha hydrogen. So aldol reaction is not possible. This is cancelled out. So next thing is Cannizzaro. So what is Cannizzaro reaction? A quick recall. If this type of or I can give you some simpler things like R1CHO 2 equivalent plus any strong base like NaOH, KOH, this can be used. So for that, what happens? At first, the COH minus attacks this carbonyl center. So O minus OH H, right? So next thing is this subtraction can happen. So OH, sorry, OH, this should be OH, this should be OH. Yeah. So OH, and one minus like this, and so this is for one molecule, and I am using here two equivalents. So you can think of like this. Let me clean things here. Yeah. So yeah. So here one hydrogen is there, and this can push like this, and this H minus can attack like this one. So if this happens, this black color molecule, what is the fate of that? R C double bond O OH, and here R CH2, it is O minus, and during acidic workup or any workup, water workup, the proton can be abstracted and this can be formed. So you can see this, if we do this reaction, so one would be acid and another would be alcohol. So if Cannizzaro occur here, the product should be pH CO2H and pH CH2H. But you can see this is not our required molecule. So Cannizzaro is also not the option. So the next is benzoin condensation. So you already can see this is the answer. So what is happening in benzoin condensation? So in benzoin condensation, the nucleophile is the nucleophile used is cyanide minus. So if cyanide minus is used, let's see what is the mechanism for that. So pH CHO. So Cn minus can attack this center and make this as O minus. So pH O minus H. So and another thing is Ca, right? So this O minus can abstract this proton and make it like this. So this is kind of unusual thing. Why this negative charge forms like this? So reason for that is nothing, the cyanide group. Without cyanide group, this is not possible. If negative charge is there, this type of resonance is there. So that's why this carbon ion is stabilized and this can be formed. So this moiety is formed, and now the second equivalent of the benzaldehyde group is uh, not group, benzaldehyde molecule is there. So this directly can attack this center. So you can see the CC bond formation is done, which is the major thing for this benzene condensation reaction. So now what is happening? pH, OH, one CN is there, then the CC bond formation occurs. So O minus pH H. Okay. So after that, what would be the product? So this O minus can abstract this proton and make this O minus. So pH O minus COH HPH, and here one CN group is there. So this OH can attack this and CN can be removed, which is nothing but our product, one keto, one alcohol, both are pH. So you can see this is the TGT which they have asked in the reaction. So that's why benzene conversion is the right answer for that. And for the Barch reduction, so I have next few sets of questions where I will discuss the Barch reduction. Although I know most of you know that, but still. And so in benzoin condition, you can see we have to use here cyanide minus. So source for that is NaCN or KCN. So you know that how toxic both are. So for that, some of them are banned also. So as the reaction is so good, the CC bond formation, but the toxicity of these reagents may create problem. So for that, I want to share one of the newest benzene condensation reaction without cyanide minus, with simple one organic molecule people have discovered and they are using it. So you can see this is also an benzene condensation reaction, but not presence of any cyanide minus, simply this molecule, simply this molecule. So this is published in JAX 2014, and now this become so popular for the benzene condensation reaction. So for that reaction mechanism, here is the reaction mechanism. So one thing you can see, the carbene is the starting point or the active species for this molecule. So how carbene is forming from here? So I am writing like this here. So this is the molecule that is used in catalytic amount here. Let's say R group, and here one counter anion is there. So here you can see one acidic proton is present, and dipA. What is dipA? So it is you no need to know the whole structure. It is just for the time being, just remember this is just a base. So what base do? They abstract proton, and as it is the most acidic proton, it abstracts proton here and make here a negative carbon ion type thing. So N double bond plus R group is there, and it is minus. So now what, as it is positively charged, so this can be go there. So if it go there, what is the form? You already have guessed, it is nothing but the carbene. So in this way, the carbene is formed in situ in the reaction mixture, and it is the active form for this reaction. So let's see how carbene is operating to do the benzoyl condensation reaction. So you can see this is one aldehyde group and this carbene. So first attack over here and make this O minus, and again for stabilization this C double bond N plus is there. So first this type of intermediate 2 is formed. So now 2 to 3, how things are. So it is nothing but this, like benzoyl condensation reaction, this proton is abstracted, and how it would get stabilized, like there CN the cyano group help, and here this C double bond N with positive charge would help. So this in this way the stabilization is done here, and you can see this inolate type of thing, and like this the neutralization of this nitrogen drives this particular step. So after that the second aldehyde molecule R2. So you can do homocoupling and heterocoupling also. Here the example is for one hetero one. For homocoupling also the same mechanism. Here the thing would be R1. So now this enolate is there. So second attack is feasible like this, the previous case. So this lone pair and this attack. So the CC bond formation is successful. You can see we have shown it in the bold form, and it is O minus R1 R2, and then nothing. This cleaving of this would lead to regeneration of this carbene molecule, and this would give our benzoyl condensed product. This is the required product, and carbene is also regenerated. So this cycle would go on. So you can see only 5 mole% of this molecule, this organic molecule, can do this step, and this is a great development of the benzoyl condensation reaction by removing cyanide to this carbene based mechanism. So this is one of the new things so that I want to include here. uh, so now let's go forward for the next problem. Yeah, please go ahead. What is the, yeah, yeah, okay, okay. So for this particular case you can see, of course the some of you may get some of the homocoupling product, but the heterocoupling product is measured. Why? Because you can see, yeah, I am explaining. Yeah, so you can see this is alkyl group and this is aryl group, right? So uh, when the first R1 is reacting with that and make this type of enolate, so it's have itself competition with that aromatic one versus alkyne one. So now generally aromatic aldehydes are more favorable for this type of attacks, so more electrophilic in nature. So so this type of moiety would attack this type of aromatic ring first, and not the not the other one. So in this way, the heterocoupling products are measured in this, and in in particular this type of reaction. So yeah, any other further clarification? Yeah, if you want to do the only the homocoupling reaction, right? So if you not, if you do not use this one, only this one, then homoalkyl thing would be major one. And another thing you can do, like in the reaction mixer, if you use at first, we what we use one of this, one equivalent of this and this carbon molecule, and after some time we add excess amount of the other one. So for that, the concentration of that other the other partner is very much greater than the homocoupling partner. So in that way, with the concentration variation, we can control the heteroproduct as major and homo as minor. But yeah, I have to say that homo hetero both are there, but some controls are there to make the hetero coupling products at the major one. Yeah, yeah, yeah. So moving ahead, this is the next problem for that. So yeah, so this is again, this is the starting material and this is the target molecule. So how can we achieve that? So this is a simpler question. With Bart's reduction we can simply can do the reaction. So but for the other reactions, what are that Nauri reduction. So this is used for reduction of keto groups. So X or any aldehyde or any keto type of molecules, we can use this Nauri reduction, and it is also the major thing about this is the asymmetric version of this Nauri asymmetric version of this Nauri reduction. It is so helpful that probably he have achieved like 95 to 99% in enantiomeric excess. So this would be I will discuss later, but for the background of this, so this is the only for the reduction of this type of molecule. So here you can see the reduction is in the benzene, the aromatic ring. So this should not be the right answer. So A is not the right answer. So another thing, the right answer would be B, as it is written. You can see. So what have you in Bart's reduction? What are the things are used? This sodium or any metals, potassium like this group metal, and ammonia. And why ammonia is used? To solvate the electron. Already you have know, I think, in where to solve when to solvate the electron, the ammonia is used. Then in the this type of electron withdrawing substrates, COOH, can the most electrophilic center we already know this. So most electrophilic center it is that. So this attack is favorable. So 1,4 reduction product is there. So this CO2H. So second equivalent of electron is there, and proton source is available in the reaction mixture, which would lead to our required target molecule, this 1,4 reductant product. So Barton nitrile ester reaction and hydrogenation reaction. So what are the hydrogenations? You already know that reduction of the alkyne groups are hydrogenation reaction H2PT6. So cis hydrogenation reaction, trans hydrogenation reactions, many of them are known. So next is Barton nitrile reaction. So I do not know many of you know or not, so I thought to include that also. So Barton nitrile reduction is majorly and photo driven reaction. You can see the H nu is used. So for this type of reaction, you can see the ONO bond is there, and here actually it is alpha beta gamma delta hydrogen is there. So at first with the photo condition H nu, this homo cleavage of this bond would happen. So O dot is formed and NO dot is formed. Now this O dot can abstract the proton, the delta proton only. So why is that, not the other ones? So because you can see, if we can see the transition state of that, if the delta hydrogen is abstracted, the transition state is 6 member. So this is the most stable one. For that, the delta hydrogen abstraction is majorly happen in the reaction, not the other hydrogen. So after this delta hydrogen abstraction, you can see OH and O dot is formed, and NO dot is already present in the reaction mixture. So now the recombination of these two radical NO and this O dot can happen, and this CN bond is formed, and it is nothing but the tautomerized version of that. Both are possible. So generally this is the majorly, this is the product, and for the hydrogen bond stability you can also say this. So this is not the concern. The thing is this transfer of this NO group to this delta position. This is the Barton nitrile ester reaction. So this is also not the correct one, as you can, yeah. Sorry. Okay, yeah. So it's a nice question actually. So why nitrile ester? So I think ester group. What is that ester group? RCOOR. So what would be the nitrile ester? Right. So I think this ONO. Right. So this type of this nitrile, and it is kind of yeah, resembles the CO group, and as this C and this nitrogen and O is bonded. So with for this comparing these two, the similarity between these two, this they have called this as nitrile ester. So nitrile are, and yeah, nitrile and C double bond N, right? C triple bond N, yeah, C triple bond N. Yeah, this reaction is also known as the simple Barton reaction or Barton nitrile reaction. So okay, I will look into it if any naming is there, and I would clarify that. Okay. Yeah. So yeah, this is our next problem. So this is also based on one Bart's reduction problem that the previous one I have discussed. Yeah. So so Michael reaction you already have discussed earlier. So Michael reaction is for 1,4 addition. So this is not the case. So acid hydrolysis is also not true for that, not here. So acid hydrolysis is not the right thing for that. Hydrogenation is also not. So batch reduction followed by acid. So how this should happen? So this is the starting material. So electron is there. So in this case for OMe, as it has plus R effect, means the thing would be the electron density of this in the ring, it would push. So this ring is actually electronically rich. And what are the positions that are electronically rich? This ortho position and para position. So what would be the most electropoor centers? So that would be the meta centers. So for that, the meta attack, the electron would attack in the meta position. So if meta in the attack is happen in meta position, what would be the thing? So here here I am attacking here. So okay, yeah. Yeah, so here the electron is attacking, so this should be here, this should be here. So here dot, and I am attacking here. So sorry for here, the things should be cleared. Yeah, so I am here, I'm directly attacking it in the meta position. So if electron attack in the meta position, so like this, right? So OMe here dot here dot, then you will know the H plus is there and one more equivalent of electron is there also. So the reduction would happen, and this is the product. And then what they have told, the acidic water, it means that some strong acid is used here, or like HCl, HBr type of thing. So this this O minus would obstruct the acidic proton, and it become protonate there. So OH, Me, and this is positively charged, and then the halide like Cl minus or Br minus can attack here and make this OH. So this is OH. So this is nothing but the knowledge from of the keto group. This now here you can see the position is alpha beta, but what we are getting is gamma delta. So here nothing, the isomerization can happen. So this acidic proton can go there. So alpha beta unsaturation is now there, and we got the target product. So what is the driving force for that? The resonance stability of this species, this continuation. This is the reason why this from the molecule prefer this form, not this. So that's why if we do the batch reduction followed by acidic workup here, we would got this particular product. So moving on for the next problem. Next problem is that this is the starting point, and this is the target molecule. So target molecule. So at first I would discuss all the things for a quick recall. So what is POP? So POP is there 1 1 2 3 2 3. So just breaking of this bond and becoming this is the normal POP reaction, and this is normal POP. Oh sorry, they have here used the POP elimination. Sorry, this is an POP rearrangement type thing, so forget this. So they have told POP elimination, right? So what is happening in the POP elimination reaction? So for POP elimination, the thing is uh, this one. If the inner two part is there, followed by MCPB oxidation, and make this N oxide over here, and with presence of heat, one cis elimination is occurring, and like this, the alkene is generating. So this is POP elimination. So you can see here no nitrogen atoms are there, so this is not a POP elimination. What is Barton decarboxylation reaction? So you can see here this this particular thing. So this is for the Barton decarboxylation reaction. This is the starting point. So how this type of things are made? So with acid molecule followed by DCC coupling with uh, this type of uh, this type of uh, this type of uh, starting materials, this can be formed to decarbox for this decarboxylation reaction. So after that, AIBN and in Bu3 SNH, the tin hydride. So with combination of this SN radical is generated. So what this radical do? This radical would sorry. So this what this radical would do? At first, this combination, you can see that SN and the sulfur bond formation over here, and one radical is generated over here. So then this radical can come here, and the homolytic cleavage of this bond, and followed by this type of relay of disconnections and recombination of radicals from that CO2 and R dot. So now R dot can abstract the H minus or H dot from this and make this RH, the RH, which is the required product for this type of Barton decarboxylation reaction. So you can see from ROH to RH it is formed, and this is decarboxylation reaction. And another thing is Chugheb elimination reaction. So what is that? And this is also the right answer for this reaction also, for this question also. What is the Chugheb reaction? So you can see this C double bond is abstract this H minus from here, and this type and some in type of the syn elimination, like here O minus did the thing, and here S minus would do the same thing and make this alkyl group, and this is the other byproducts. So here you can see the same way. This here is an proton over here, and this S minus would abstract this and this. So in this way one sim elimination can happen and make this product. So for this case the right answer would be to get elimination reaction. So moving on, what is so this is the next question. So you can already see for this question the right answer would be A. So how this would happen? 1 1 2 3 2 3. So this is the starting material and this is the target. So here first this and this. So here I am writing like this. So keto is formed and this is formed. So it is normal Claisen rearrangement reaction. So this is our right answer. So what are the other things? The oxycope rearrangement. So at first we need to know what is cope. So cope is also related to the Claisen rearrangement, the 3,3 sigmatopic shift reaction. Sorry, 3,3 sigmatopic rearrangement reactions. So here I am giving an example of one cope reaction. So you can see uh, 1 1 2 3 2 3. So if this type of reaction happen and made this, then uh, the reaction is known as cope reaction, and here is anionic oxycope. What is that? So I have written here what is anionic oxycope. This is anionic oxycope. So what is oxycope? If KH, sorry, the hydride salt or any base is not there, means only OH is there, and thing proceeds without making this type of anion here, that would be known as oxycope reaction. And as here KH is used, so this O minus is there. So it some way it can accelerate the reaction and make this uh, disconnection of this and formation of this bond more feasible. Like this way you can see, as this O minus is pushing electron over here, so making this arrow pushings are more favorable, and in this way this is known as oxycope reaction, anionic oxycope reaction. So what are the two other things? Ireland Claisen and Johnson Claisen. So Ireland Claisen LDA is used in presence of TMSCF. So this type of OTMS, and in presence of this LDA, the alpha hydrogen abstraction like this, and here that TMS formation, the enolate thing. So this over here. So if we use this particular type of condition and make this like this known as Ireland Claisen. So what is Johnson Claisen reaction? So here to form this type of precursor for the 3,3 rearrangement, this type of uh, reagent is used. So how the things are formed? So in presence of acid, actually the reaction proceeds. So in presence of acid, one of the OMe group removes, and OMe OMe and one methyl is there. So it is like this, and this hydroxy group over this attack over this electrophilic center, as it is feasible. So it is not H, it is CH3, right? It is CH3. CH3. So if this attack happens. So what is the product? So you can see this is R1 double bond R2. Here OMEs are there, OME, and methyl like this. So I have purposefully written like this so that I can eliminate. So this 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 type of thing happens in presence of acid, as acid helps to remove one OMe group, and you can see the double bond OMe is formed. So this is the precursor for the 3,3, and then 3,3 rearrangement happen and make this molecule. So if we follow for making the precursor of 3,3 rearrangement product, if we follow this particular protocol, this is Johnson-Claisen rearrangement. So as I have talked both of the Ireland Johnson, the other thing is the Essen-Moser-Claisen. So in this way, making of the particularly this this intermediate, there are many variations for that, and these three are the most popular ones. There are many other variants are there. Many of probably still people are discovering. So there are many variants, but these three are mostly used and well established. So I have included these three. So uh, so yeah. So so for the Essen-Moser Claisen, we you can see some only some functional group modification. So without OMe, as Johnson Claisen, there is 3 OMEs. So here with one OME is not there, in Me2 is there, and rest of the things are same. So this particular variation of this R group and making this in Me2 did the another naming, which is Essen-Moser Claisen. So how these things proceeds? Here also acid is required, and this also proceed to, I have shown in Johnson Claisen. Same way it proceeds and make this precursor for the 3,3, and you can see 1 1 2 3 2 3. So this 3 3 rearrangement is done and make this molecule. So this is Essen-Moser Claisen rearrangement. So these are the other options. You can see they are not the right one. So one is the correct, which I have discussed earlier. Yeah. So this is the next question. So what is the so the following retrosynthesis? So what particular reaction is the right one? So these two are two starting materials, and this is our required target molecule. So what is the right product answer? So you can already see the answer is A. Let's see why. So Michael reaction I have already discussed. So it is only 1,4 addition product, which is not the case. Aldol have already remember, it should be not the product. Another thing is net. So these two I would be discussing what are these two reactions. So for at first Kore Tchaikovsky reaction. So the right answer is that. So I can directly show you over here, or so at first what I am doing, I would show you what is Kore Tchaikovsky reaction. So Kore Tchaikovsky reaction, actually they are the reaction with sulfur ylides. So you can see here one more oxidation state above and one oxidation state less. So here it is normal sulfur and sulfur, and here it is in oxide form. So both reaction condition you can see almost not almost similar. It is heating condition and it is 0 degree to RT. So here what is the active species, it is sorry, S plus O minus, and here carbon minus. So this is for this case, and for this case it is like this. So now you can see this this carbon center is majorly stabilized by this CO group. So we can call it as an soft center compared to this one, as this is not stabilized, as there is no oxide group over here. So a carbanion can't be stabilized like this. So this is soft. So this is soft nucleophile, and this is hard nucleophile. So I am explaining this with hard soft uh, concept, and homolumo can also be thought, but for that solving approach, for the problem solving approach, this is faster approach, so I am showing it like this. So this is softer nucleophile, this is an hard nucleophile. So in this molecule, what is the hard center? This is, as this is more electrophilic in nature, so it is adjacent to the carbonyl, and this is like this. So this is the hard center, and this is soft center. So in this way the reduced selectivity actually dictates. So if we use soft nucleophile over here, so soft combination would be favorable. So this would attack over here. So then what would be the product? So pH, double bond of pH, and here is, sorry, at first CH2 is there, CH2 positive charge, and methyl. So it's like this, right? So at first this attack is there, and negative charge is generated as this opens up like this. Then this negative charge initially attacks the CH2 center and attack like this, and make a 3-member ring over here, 3-member ring over here, and this is the byproduct. So for this case, for the software one, this center attacks, and this type of 3-member ring forms. And for the harder nucleophile cases, so then this 1-2 addition is happening like this. So that is so here I am showing. So pH, COPH is here minus. So this will directly attack over here and do this. pH O minus, pH, and S Me2 plus. Now this O minus can attack over here and make this. So here one epoxide ring is formed. You can see if we use this, and if this softer or the stabilized elite is used, so this 3-member ring is formed. So this is an well established thing, and this reduced selectivity actually works pretty well. So now look at the our question. So here you can see for elite there is no oxygen, right? So this is an unstabilized or destabilized elite. So for that, this should directly do the 1-2 addition. And here one thing also, that no question of no other electrophilic center is there. So for this case it is more easier. So yes, and I am using it as R. So this is attacking over here. So this attack is there. So what is the thing? So this this here it is aldehyde, so minus, and here it was is like this, right? So now the nucleophilic attack, removal of this group, make this epoxide uh, epoxide ring over here. So I am only writing like this. So this is the target molecule. So in this way, the right answer for this is Chekhov-Chekhovsky reaction. So we have discussed these three options. So another thing is left. What is Neff reaction? So let's see what is Neff reaction. Yeah. So this is the Neff reaction. You can see. So Neff reaction. So this nitro can be directly transferred to a keto group. So what are the reagents for that? So only base and acid is required, and things go pretty well. So if we at first treat this molecule with base, so NaOH. So first what would happen? One, uh, proton abstraction, that is I'm writing. So this is an very acidic proton, right? So OH minus can easily abstract this proton and make this C minus over here. So this can further stabilize by the nitro group, right, like this. So this is, they have written like this, the at first this and the stabilized version like that. So with presence of base, at first this thing happens. So now next thing, so proton is there. So this OH would abstract one proton and make it OH, and then this O minus is also would abstract another proton, as we are using, you can see H2SO4, very acidic thing, very acidic, very strong acid actually. So you can see both OH, right? So as you can see that in OH and H2SO4 is used over here. So in the reaction mixture, water is there. So this water molecule can now attack over here. Why it is attacking? To neutralize this N positive and make this neutral. So H2O can attack over here and make this CO bond and make this neutral. So the next thing is happening. So to for stabilization, the one H plus is removing and becoming OH, like this you can see. And another thing is also happened here, this H2 removal, so make this in double bond like that. So here the lone pair of that OH can push this and break this CN bond and make this type of HNO thing, and one C double bond is formed due to this type of arrow pushing mechanism. Then only thing is left to neutralize this O positive to uh, keto group. So this is nothing. So proton removed and the keto group is formed. So another thing is, this is not a stable form. So this could do several steps of reaction, and it removes S into S byproduct. So this is Neff reaction, quite a new reaction probably for many of you. So NO2 can directly transform to keto group. So this is the thing of the Neff reaction. So you can see, so Neff is the not the correct answer for that. So it is correct. So in this way we can easily solve this type of question. So these are I am just recalling all the name reactions, not all the most of the common or known name reactions. And for the next session we would most mostly focus on the retrosynthetic uh, disconnection strategies. So yeah, so this is the next question. So you can see this is starting material and this is our required product, the target molecule. So first option is ozonolysis. So you already all of you know what ozonolysis do. It keep the olefin group and make ketones. So this is probably a very well known reaction. So mechanism probably all of you know. So it go to an ozonide formation. So I am not discussing it in detail as it is pretty well known reaction. So next thing is this LG oxidation reaction. So what is that? So this is the mechanism of that. So ruthenium oxide or osmium oxide are used for uh, this type of LG oxidation reaction. So here you can see um, here directly this diol is given, and with the ruthenium oxide and osmium oxide, another thing is also in the this given is NaIO4. So you can see NaIO4 can make this type of adapt with this diol compound, right? So now in this type of this diol compound, so what will be happening? So this sorry this and here breaking of this. So here the keto bond is formed, the the I oxygen bond is split, I oxygen bond is split, and C double bond is formed. So NaIO3 is the byproduct, and 2-aldehyde is the 2-end aldehyde is the our target molecule. And here also you can see this is the thing. Only thing is in our question two methyl groups are given. So if two methyl groups are given, the thing should be the same. So we can say that this is the right option for this reaction. So for the full version of the reaction, it we can also give it from this alkyne group also, right? This can be another version of this question. So you can see with the alkyne molecule with ruthenium oxide or osmium oxide, at first this diol formation is happening like this, and here also NiO4 is helping to regenerate the ruthenium oxide or osmium oxide, as these are costly. So that's why it is used in catalytic amount, and this is in equivalent amount. So in this way the thing can be proceed and make the LG oxidation reaction. So what are the other options? We are seeing that Jones oxidation reaction and Swan oxidation. So what are those? So let's see. So this is Jones oxidation reaction, right? In Jones oxidation, what is the product for the oxidation of the alcohol? It is acid. You can see with chromium trioxide in H2SO4, the ROH is converted to and carboxylic group, acid group RCO2. So what is the mechanism? With CrO3 at first, this type of attack is happening, and O-Cr bond is formed. Then when this formed, this hydrogen become pretty acidic. So water I can also abstract this. So in this way, this H can be removed, and the this moiety can be formed. So now one aldehyde group aldehyde as one intermediate is generated. Now in presence of this type of acidic condition from epoxide, the further gem diol from is also can be formed, and after that the same way that CrOH like this type of things can be formed, and this proton is there, it is acidic, so water can abstract, or it it can remove at H plus. So in this way the acid is formed. So for the Jones reaction, the primary alcohol directly converted to carboxylic acid product. So this is for Jones reaction. And Swan oxidation. What is that? So this is Swan oxidation. So here uh, any not mostly no chromium based things are used, only DMSO and oxalate chloride. So structures probably are given here. So in the particular this type of condition, you can see the OH and combination of this, how this is formed. This is actually with DMSO and this oxalate chloride, COCl, COCl. The combination of that, this active species is formed, which is responsible for this oxidation. So this OH can attack the sulfur center as it is positive and make this type of OH and Me plus bond, and Cl minus is there. So Cl minus can abstract this proton and make this allopocene mode. They have already shown in presence of base, as you can see triethylamine is there, can be used and make this type of ketone. So this is Swan oxidation. So if we have so for the question solving, you can already we have got the answer. For clarification of these two name reactions, I have discussed these two also. So moving on. So you can see that this is our next question. So this is starting material and this is target material. So how can we make it from there? So what is the change? In starting material this is keto, and in the target molecule it become alcohol. And the interesting thing is that here is both olefin are unaffected, should be unaffected in the target molecule. So for that, these are the options what we can we would choose from here. So what would happen if we use LH? So LH, you already know Li and aluminium. Sorry, here minus and 4H are there, right? So LiLH, and as it is a strong, very strong nucleophile acts as H minus. So if we use LH over here, what would happen? That one thing is that this alcohol is should be this ketone should be removed, should be reduced to alcohol. This should occur, obviously this should occur. So I am writing over here. You can see this here. Oh, sorry, probably I have given one carbon bond extra. So here 7 member is right. So here double bond, here, yeah. So here, here rest of the things are there. I am not writing here. So you can see these three are conjugated, right? So this you can see like this, all are conjugated. So for that, this is also an electrophilic center, this is also an electrophilic center, and obviously this, and the, and LOH in LH H minus is 4 H available, H minus hydride source are 4 LLH whole LILH 4, right? So if we use LH over here, so this H minus can attack here also, and easily can reduce this bond, and this bond. So if we use LH, the whole the global, I would say the global reduction can occur, and olefin should get affected if LH is used. So but in our target molecule, you can see that both olefin should be remain in the olefinic form, not reduced form. So for that, LH cannot be used. So this is one thing. So if you use borane, also borane, you can you are already know, right? BH3 or NaBH4. If this type of species are there, uh, they are very reactive to alkyne groups and make this type of BH2. Here you can use other things with H2O2. You have read already idea. So alkene groups cannot survive in this condition. And in an naphthenic, again the same case. Electron, it is very reactive, and it would definitely attack this position, and make or reduce this. So also this also cannot be used. So for that, the best condition to reduce only the keto, not the alkenes, is Luce reduction condition. So what is the Luce reduction condition? NaPH4 and CCl3. So here this cerium plus play a major role over here. So I am simply drawing it like this, as the simpler form of this molecule, right? So what C3 plus do? C3 plus make adapt like this, right? So if this happens, this center becomes so much active, and this become less active. So, and in presence of NaPH4, H minus can only attack this position, as C3 plus make this center so much reactive, and compared to this and this. So in this way, CCl3 and NaBH4 condition, only this keto group got reduced and not olefin. And also for this case, also time is the one of the major thing. This type of Luce condition reactions are reduction is very fast, almost from my experience I have done this type of things. So 10 to 15 minute whole reduction is done. So if we keep it for longer time, so this olefin may also disturb. So in the particular this reaction condition, the keto is majorly reduced, not this. So for that case, for these reasons, the Luce reduction condition is best to reduce only the keto by with unaffected alkyl groups. So this is the so D would be the answer for the question. So this is one next problem. So this you can see this is used in 2 equivalent and this is used in 1 equivalent. So what is the mechanism of that? So Cl, CO, Cl, right, and here I have this. So this lone pair and this acid chloride group, they are pretty reactive. So this is a pretty fast reaction, I would say. And make this CO, CO, Cl. Sorry, sorry. Here OH should be there. So O is there. Here benzene ring. Here methyl. Now the second equivalent of the starting material as equivalents are used. You attack there and do the same thing and make the molecule. Right. So this is one straightforward mechanism how the product is formed. So, but you can see in the all four options the products are like this. So here actually question is the stereochemistry of the product, right? So you can see this is a chiral center. When we are doing the reaction, this chiral center is not affected by anything. So this chirality of this molecule should be retained. So this question is just a stereochemistry based question. So we need to just check the nomenclature of this. So let's see what it the nomenclature for this. So this is totally prioritized 1, 2, 3. So this is like this. So this is S, right? So now we need to check all the four reactions where both this center and this center should be SS. So now let's check here 1, 2, 3. So this is clockwise, but H is above, which is least prioritized. So this is S. 1, 2, 3. Again, this is clockwise, so this is S. So this is our right product. So this is we have got, but let's check for the other one also. So 1, 2, 3. Right. So it is like this R, but here it is below. So this is R. Here also same R. So you can see this is inverse compared to this. So this should not be our product. So P is not the product. Here also this is R, this is S. This is fine, but inversion of this should not be there. So this is wrong. C also is not the product. So this is S, this is R. So here also this is not matching. So these are not the product. So only product is SS. So just to the RS nomenclature of the centers where it is SS, this should be the product. For all the other combinations, so they are not the product. So this is just a stereochemistry based question. By nomenclature you can easily predict the reaction, the right answer for that. So this is our next question. So here you can see PTSA. What is that? Para acetyl sulfonic acid. So this is the structure for that, and this is a pretty acidic or highly acidic molecule. It is solid and highly acidic molecule. So let's see what the acidic thing would do here. So OH, right? So you may be thinking that which OH would attack abstract proton, right? But you can see one C2 axis is there. So it is a C2 symmetric molecule. Means if you rotate the OH would the OH, if you rotate this, the molecule which we would get is the same. So it is the C2 symmetric molecule. So this OH and this OH, they are chemically equivalent. So no question of the which OH would abstract the proton. So any of the thing you can go ahead with any of the hydroxy group and end up with the same group. So let's see, I am doing it with this one. So this become OH2 plus, nothing but a different group. This is OH, this is like this, right? So now question is, elimination would occur first here, right? So now question is, which is the method? So if this removes, it would give us this molecule, and which is stabilized due to this conjugation is there, so it is stabilized. This is one part. Another, they have shown one epoxide formation, so you can also think of that it attack here, right? But no stabilization is there, and 5,3 epoxide is pretty strained thing, so this should simply more stable than this. So this is the right product. So another thing they have given this like this, right? So actually here what is the problem should be the stereochemistry of this, because you can see if you do the thing with here and eliminate this, this should be below the phase, so it's not above the phase. So that's why B is not right product. C, you can see not stable, and so the right answer should be A. So here also stereo and elimination based question, so you can easily you can easily solve it uh, by RS nomenclature and simply the elimination way. So moving forward, yeah. So after the quick recap of some of the name reaction, now I would do some course based naming things. So uh, what are the functional group addition, functional group disconnection, this type of reaction, because these are the simple tools you would going to need if when you would approach for a bigger molecule. So here there are simple small molecules, it is easier, but when things are much larger like natural products, this type of naming, the short forms, they are required to uh, chop the molecule in small pieces, and so that you can synthesize this. So let's see. So this is starting and this is target. So what is this kind of reaction, right? So you can see epoxide, right? So this the difference between starting to target molecule is one oxygen is extra, means epoxide epoxy group is adding or extra over our starting material. So this is functional addition. So this is the right product. So what is RGD, ring disconnection? So I can uh, give example here also. So if we do, let's say this is the ring, if we disconnect this bond and make this type of things, right? Here it is synthons, so minus nothing like that. So if this I would do this operation, so this would call ring disconnection, as I am disconnecting a bond in ring, so that would be ring disconnection. So chain disconnection, let's say here it is and ring. If without ring we have molecule like this, a chain, simple alkane chain, and then if we disconnect like this, so this would call as chain disconnection and functional group removal, right? So let's just reverse this or here addition, so this can be told here. So functional group removal, you can think of like here you have one fluoro compound, from here you are removing fluoro and making this. So this is for forward. So if in retro you want to do this and remove one functional group, that would be known as FGR or functional group removal reaction. So now this case, so look, CA, so this is starting and this is target. So what is the change? The cyanide group is converting to CHO. So how can we do that? I am doing some reactions also with naming. So with simply divalase, you can do this type of reaction, cyanide to CHO. So this is interconversion. So cyanide is interconverting to aldehyde. So this should be FGI. You can see functional group interconversion. So ring disconnection is not the thing we are doing. Chain disconnection is also not doing. Functional group removal we are not doing. We are interconverting, right? So if let's say without CHO here H is there, then we can say functional group is fully removed, then we can say that FG. So here the right option would be D. Now this you can already probably guessed with this is an normal demand till solder reaction, right? 4 plus 2. So here this is starting materials and this is target material. Here you can see functional group removal, so we are not removing anything. Chain disconnection is also not doing the disconnection. You can say without if we disconnect only one bond, then you can call it ring disconnection, but you can see both we are disconnecting two bonds and generating two bigger moieties, right? So these moieties are called appendage. So that's we are for that we are the naming we are calling it as appendage disconnection reaction. So this is you can see this is an chain and we are disconnecting this bond, so it is nothing but chain disconnection reaction. So this is the right product. Functional group removal is all wrong. Appendage disconnection, ring disconnection. These are simple simple naming related questions. You may seen this type of question in your assignments, so that's why they are here. So next thing, Again you can see without the ring is not there, chain disconnection we cannot say, because the longer chain it is quite controversial which is the longest, and so chain disconnection is not that. So again you can see two bigger moieties we are generating by this disconnection of this bond, the gill solder, and so it is called as appendage disconnection. So right option would be C. Again so I am not discussing forward actually, so uh, mainly already know this is wheatic, this is olefin, so this is an wheatic reaction. So anyway, future classes I would discuss these questions, and some of them have already discussed also. So here, how can we from that? We need to make an enolate. So with minus or any other strong bases, in we need to generate an thermodynamically stable enolate. So this is thermodynamically stable. So this is TCP, and if we generate enolate here, this is ACP. So if we need this, we need to do very low temperature reaction with LDA like bases, 72 minus 78 degrees C, and here you can do 0 to R. So in this way, with your selectivity we can easily achieve, and this enolate, the TCP control enolate can attack over here, and normal CC bond formation would lead to this product. So this is the next question. So here you can see from the starting material to target molecule. What is the difference? The difference is this keto group is fully removed, and this becomes CH2. So what? So with the naming, you can see this is functional group removal, as keto is completely removed. Functional group removal reaction. So A should be the right answer. So how can we do that? So there are many things, many way you can do. The most famous are like Wolff-Kishner reactions. You know these things. So simple things like that. You can remove the keto to CH2. So this is the next thing. So you can see this is starting material and this is starting. So what are the difference? So you can see nothing is removing or adding. So no functional group are all same. So B cannot be the right answer. Nothing added. So functional group addition should not be the product. Or removal is also not. So isomerization based transformation is the answer. So here the thing is the double bond is Z, and here E. So only this isomerization is happening. So how can we do that? So this type of cases actually each new can do the trick. So if we radiate the molecule with right frequency, and this type of radical is formed, then you can see this is not stabilized. So this should try to be in stable form. So this CC bond can rotate like this, right? So after rotation, this type of things can be formed. Then again the recombination will lead to target molecule. So this type of simple things are there. This can easily be done. So this is, you can see this is NO2 to keto. I hope all of you can correlate this. I just few minutes earlier I just described this. This is nothing but a NEF reaction. I hope all of you remember. So in basic and acidic condition, the NO2 uh, can be transformed to keto groups. So here functional group addition, of course, functional group is adding, so it is right. Intercorporation is also there. And transformation based approach, obviously this is. So this is all of the above should be the right answer. So for if you have for quick recap, I am again going to the NEF reaction slide so that you all can uh, correlate. So here discussed earlier the NEF reaction. So you can see the functional group is adding. So and this is transformation based, and NO2 is removing. So everything is there. So that's why all of the above answer is correct. So yeah, so it is done now. 9. Let's see what is that. So this is a synthon, and this is from starting material. This is our target molecule. So the following retro as shown is an example of use of synthetic equivalent. Obviously, we need to if it is one equivalent, we have to use it in one equivalent. If we do not maintain the ratio, let's say if we use two equivalents, so here CO can be formed, and no, and this ring should not be formed if we mess up with the equivalent ratio, right? So synthetic ratio is right. So it is an example of ring disconnection. Obviously, ring is disconnected, ring disconnection, and plung and yeah, we already know, but still I am discussing. So in the generally this type of uh, carbonyl molecules, these centers are electropositive, right? So when we we want to generate this is our target, so we generally prefer to keep this syntron as positive, right, and this as negative. So this is the conventional approach. So this should be uh, here this is positive, but here you can see it is negative. So we are reversing the nature of an the carbon center of an carbonyl. So that's why it is known as unplug anion or an unplug effect. So how can we generate this type of, so for this it is nothing RO in chloride halides, right? So normally these chloride halides stars can be used for this, but for negative cases what we generally use this type of things, right? So this is an acidic. So this is the anion. So in this way we reverse uh, the electropositivity to electronegativity, like in this for this carbon center. So this is that's why you can generate, and after the protection of this we can get the keto. So that's the general approach for this unplug effect. So C is also correct. Yeah. So the answer would be all of the above are correct. So next thing is this. Yeah. So let's see how to approach this. So this is our target molecule. So TGT. So CH. So we can disconnect but this like this should be double. Yeah. So again it is uh, so as I have on the previous problem I have discussed the unplug effect. So here I am doing the CHO minus, and here positive. This is one synthon. How can be this one as positive? So this is how the retrosynthetic plant is happening. So first disconnecting this bond, this should lead to this positive thing. How this is can be made. So this is, should be the starting material as it is positive, and how this can be a can we get. So this simply can be from this, right? So let's now look at the options. So for mild cation, so if cation, so CO plus should be there, right? But we are using minus, CHO minus. So not for mild cation. Acetyl cation. So acetyl group we are not cleaving, it is not there. So acetyl should not be the case. So for mild anion, yeah, should be the right answer. So here also we have generated an formyl anion, which is unplug effect. So this should be the right way to do an disconnection and forward and move ahead for the synthesis of your target molecule. Uh, so let's see what is the time today. So yeah, so probably these 2-3 questions I could, yeah, I could finish actually. Yeah. So let's finish this quickly. So you can see the following transformation achieved by the reagent. So you can see it is not double-headed arrow. So this is not an retro arrow. So the forward thing they want to know what they have done, we can do to make this starting material to target molecule, right? So let's see the options. So if first they have do this Wittig treatment. So if we do that, let's see what would be the product. So this keto, and this is our Wittig partner, COM. So this should attack here, make this O minus CH COMe here, PPH3 also there. So this. So now this attack would be there. So here 4-member ring formed, PPH3, here CHCOMe. Okay. So now this would lead to double bond COMe. This is the first treatment is done. Again they have the addition with formyl anion. So formyl anion you have know what is formyl anion, I have discussed earlier. So this formyl anion addition. So now CHO and here COA. So this should be the reaction sequence we are following in the first condition, and we are getting the same product. So this should be our right product. So this is, so let's see other options. So CHCO2ET. So no Michael addition. So if we do the second condition, the reaction would stop in this form, right? CH and COOET. So this is not our target product, aldol and Wittig. So aldol and Wittig should not be possible here, because if aldol we have done, so this anion, the functionalization of this it can be occur, so many products can be possible. So this is not the case. Michael reaction is also not the case. So the right combination would be A, not this. So the product should be A. So right now I am stopping here as we have 4 minutes left. So yeah, so I am stopping now. So if you guys have any question, can you can unmute yourself and ask, or you can write me. Actually, I have given you the mail address, so you can write here or in the chat box. You have any doubts regarding the course, the lectures, the offline lectures. If you face any problem, you can directly tell here, or I am uploading it in YouTube. You would get the link, so there you can comment. So if you have any doubt, just contact me. I would happily happily address those questions. And today, thank you all of you for joining. And okay, I am writing it in the chat box, right? Oh, okay. Yeah, I will be uploading in YouTube, and NPTEL they would mail you the links. You can and it is fully recorded, so you can easily in your convenience you can check there, and you can comment or make in the next season. Yeah, you can. It would be shared. Don't worry, it would be shared in NPTEL would share it, and everything is documented. Do not worry. Yeah, and thank you all of you for joining. Yeah, so Vidya, you have raised your hand. So any questions or doubts? Okay, so yeah, I have written no in the chat box. You can see, and in my slide, I am sharing in my slide in the intro in the first slide. It is also written. So do not worry. So anyway, today's time is up. So thank you all of you for joining, and I will see you in the next class. It is next Tuesday, same time 6 to 8. So bye and happy learning.